applause because your Uber is here. Please, Karen.
Thank you. I was really expecting Uber jokes by the end of the presentation, but yeah, it is what it is. All right. Layering is the common thing in the industry. We can consider layering when we want to stop maintaining an API that we don't like for whatever reason. It's hard to maintain, it's hard to onboard, it is easy to abuse, and then we build a new shiny API on top of the old one, and we migrate all the callers to the new API, and we ourselves use the older one in a right way. That's one example of layering. If we talk about operations, another example of layering is that there is a metal machine which runs Linux. There is a KVM on that Linux which runs VMs. There is a, I don't know, Mesos or Kubernetes on that VM which runs pod. And you as an application developer, you are abstracted from all the heaviness of the infrastructure, and the only thing you care is to build that Docker image and just let it go somewhere and let the ops guys figure out how to not break it. Sometimes we can also use layering to build a storage that provides guarantees that the existing ones do not. And I call such thing a colossus on a feet of clay. If we speak about eventual consistent storages, they are often, sometimes by mistake, interpreted in a bad way. Like, that's unreliable. I cannot use that for payments. Jesus, no, it's eventually consistent. Eventually consistent is your friend who owes you money. He will return them just someday after, which is fine. I mean, he owes you $100. You will get them. The problem begins if you keep giving him money, then you don't know when and how much he will return. A strongly consistent system is more of a bank on a deposit. You get your percentage fixed by schedule. You know it's going to happen, if it's not a Swiss bank, of course. So this is what I want to talk about today. I want to talk about colossus with a feet of clay. A strongly consistent caching system on top of eventually consistent caching system. And because the presentation itself assumes some sort of knowledge, I still want to use this and abuse this time to tell about consistency yet another time. I assume everyone in this room understands the concept, but the good things should be repeated if they can. I will introduce you to the problem and how it is solved, or should I say not solved, by Redis Cluster, and what the strongly consistent solution looks like, and what did it cost us, my team to be precise, of course, not like the whole humanity or something. Consistency refresher. I have to apologize for what you see on the screen, because consistency as a term is heavily abused. If you read consistency in the explanation of CAP theorem, that's one definition. If you read consistency in ACID acronym, it has slightly different definition. That's because, in computer science, we often reuse the same term over and over again with our own definition for whatever reason, but that's fine. For the sake of exercise, let's agree on the following statement. When we say strong consistency, we mean that we always get up-to-date, accurate, correct data as soon as the write is complete. And complete is another overused term, but let's not get into that. Eventual consistency means that at some point we may get, remember your friend who owes you $100? At some point we may get the most accurate and up-to-date data. And of course it is way more complicated. This QR code points to the Jepson website, which lists, I recall, 12 consistency models, at least. Wrong one. And when we say consistency, when we say distributed systems, of course, a wild CAP theorem appears, which states the following. The distributed system has three qualities or three attributes. Consistency means that the distributed system will return you up-to-date, accurate, actual data as soon as the write is complete, momentarily as the write is complete. So if we say take 1 nanosecond on the write, and then after that 1 nanosecond we perform a read, you get the actual correct data. Availability means that the system always returns either a response or an error. It never fails. Returning an error doesn't mean it failed. Returning an error is considered a working system. Partition tolerance means that the system can tolerate network delays or miscommunication between the nodes of that system. So where's the catch? The catch is that CAP theorem states that a distributed system can only have 2 qualities out of 3. Which means we can either have a consistent and partition tolerant system, we can have an available and partition tolerant system, we can maybe have a consistent and available system, although I would be surprised if I ever see such system in production. In a harsh reality, we have either inconsistent available systems with partition tolerance in place, or we have consistent unavailable partition tolerant systems. So with that theory, let's move on to the problem. And I would like to express the problem in the form of the data model. So the data model that you see on the screen is a basic key value or a dictionary data type, which uses the following attributes. The user ID is the part of the primary key. I will use DynamoDB terms here. DynamoDB is the NoSQL fully managed database from AWS. The partition key is the user ID. It defines on which shard the item will land, the database entry lands. The item ID is the sort, or also called range key. This is an indication of an exact entry in the database. And together, the user ID and the item ID form a composite primary key. We can query the exact entry using both user ID and item ID, or we can get all the entries for the given user ID. The version means the existing version of the database entry. The system supports versioning, and every update basically creates a new version. If you add an attribute to the entry, it's a new version, and the older version is being written into the history table. The versions, the updates are always incremental. The version never goes back. The version always goes up. Schema is the name of the Apache Avro schema name. The database, the payload, the actual data that we're interested in is Avro, Apache Avro encoded binary. And the schema represents the name of that binary, and the record is actual binary encoded information. And by the end of the document, we have 3 Unix timestamps: created it, updated it, and deleted it. And deleted it works as the soft deletion marker. That means that when we query the API, if we don't explicitly say, I want to see the deleted items, they are being filtered by that particular attribute. Low-level part is done. Let's move on to the high-level part. So the service itself, which is the problem in question, is the storage backed by DynamoDB. It is a read-heavy storage. P99 read RPS is 30K, and by the last year, I've seen spikes to 170. The storage is used in payments onboarding in processing, which means we need strong consistency. But the data set itself is not too big. I mean, 5 terabytes. If your laptop has more data than this storage, I believe. The system implements the CDC pattern, which stands for change data capture. Every time you make a manipulation with the data, the new event is being produced, which is used internally and externally. An example of internal usage is writing the previous version of an item in the history table. And because we use Dynamo, we are not protected from the famous hotshot problem. The hotshot problem of DynamoDB occurs when you have unevenly distributed data. When a given user has a lot of items, and that user receives a lot of read requests or a lot of write requests, the DynamoDB's API will throttle you with a limit of, upon a limit of 1,000 requests per second on a shard on writes and 3,000 requests per second on read. And this is happening, so we are suffering from the hot shards. Our P99 latency, because of the DynamoDB response plus the inter-data center direct connect whatever connectivity, takes about 100 milliseconds, which sometimes is not unacceptable. But what is really unacceptable is at some occasions it even has 1.5 second, which is, come on, Jesus. So we need the consistent single-digit latency while keeping the strong consistency. Who said YDB? When we say single-digit latency, I think of in memory. When I say in memory, the Redis comes to my mind because, I mean, everyone knows that the Redis is the best ever caching system with a lot of things. And, I mean, it may be true. So Redis is a low-latency caching system. That is quite known. It supports key values, the data model, which is similar to the one that I just presented you to. It is highly available in the clustering mode. It has built-in sharding. When we run Redis in the clustering mode, the caller, the client library, when connecting to the cluster, we download its topology, and it will know which node has which subset of the data, which is awesome. We don't need to build shard-aware driver. It comes out of the box, which is great. Which is not great is that the Redis cluster is eventually consistent in some cases. And these cases are obviously manual resharding event. Imagine that you filled one of the nodes with too much data, and now you have 1 terabyte of data with all the risk going there, and 100 gigs here and 100 gigs here. So you can invoke manual reshard, which will move the data from between clusters, thus introducing the eventual consistency, because the driver, the caller's driver, believes that the data is here while it is in here and is still moving here around. Another is one of the nodes downtime, like outage or an eviction, and the replica promotion. Redis implies asynchronous replication between the leaders and the replica nodes. And if the outage happens here before the data reaches the replica, and then replica is being promoted, you get stale data or no data if it's a new database entry. There is a way to protect ourselves, which is introduced in a wait argument in the command. We basically instruct the caller to wait until the leader and the replica, or X number of replicas, receive the data set, so receive successful writes. But that heavily impacts the write flow. That means that our reliability of write operation is one node and multiplied by all other nodes, including latency. And still, if you use multiple replicas for a given leader, if you have one leader and they are using multiple replicas, Redis, in an event of node eviction, will apply the best effort to choose the most fittest node. But best effort never means guaranteed. And when we say strong consistency, we want guarantees. Yeah, I need my money today. So the reason why I expressed CAP theorem yet another time, although I believe you all know that, is because in reality we have AP systems and CP systems. Redis cluster is an AP system. We need consistency, so we will make Redis cluster instead of AP system, we will make it a CP system, which is never achieved by a single cluster. I mean, we are not forking Redis and building it from scratch. That's not happening. But what we can do, we can use multiple Redis clusters. I mean, so I can run as many clusters as I want. Try to block me from that. And I can call all of them at the same time, or in parallel, or sequentially. That's up to me to decide. And what I can also do is to use something as a mediator in an event of concurrent access. If one of the clusters has one set of data, and another cluster has slightly different set of data, I can use something which can tell me which is true. And I know that my version number is always incremental. So if I have the latest version number, this is the most accurate data possible. So the version number will be the mediator in an event of concurrent access. But we need to refactor our data model a bit. So in Redis, we will have two kinds of data. The first one will be the actual payload. The user ID is still the partition key, or actually in terms of Redis, is going to be the hash itself. The item ID is going to be the key in that hash, the dictionary key. And every other attribute is going to be just a base 64 encoded data written as the value. If we want to read the data, we use, or write the data, we use basic Redis commands, hset to write the data, hget to get the single item, and hgetAll if I want to get all the items of a given user. Works well on paper, in production too. But for mediation, I want to build a reliable way to write the version. So I will introduce another data type, which I will call sorted. Well, I will not call it a sorted set. It's the Redis's native supported type, sorted set, where the user ID is going to be the score, the name of the sorted set, and the score itself is going to be item ID colon latest version. When I want to write the latest version for mediation, I will use zadd user ID, and I will use this tiny GT argument. GT means greater, and it is a internal server-side comparison operation, which lets me write explicitly the latest data, and if for some reason I write the version, which is not the latest, so let's say I write the version 8, while the version is 10, the write does not happen. And if I want to read a single version, well, the version of a single item, I will use zscore. If I want to read all the latest versions for all the items for my user, I will run zrange with scores argument. You notice that we manipulate the data slightly different here. And because we need to rely on the metadata, we need to apply the following caching strategy on with Redis. We need to apply write-through. That means that our write flow will have two stages. One is going to be fail close. That means that if during that phase there is at least one error or a timeout, whatever, we return an error to the upstream caller. And we begin with writing the metadata using the zadd command. Next will be the actual write to the database. The call itself doesn't make sense if the database is not updated. If these steps were successful, we will write to the actual data to the cache. We will write the data using hset, and then we will set the TTL. If one of these steps fail, we just log an error and we're fine. And these steps happen with all the clusters in questions, all the Redis clusters we want to introduce in our caching system. The read flow will also be different. We will first read the metadata, zscore or zrange, as mentioned before, and we expect to get a successful result, well, not an error, a response from the clusters that we need. We will read the payload, the actual data from the clusters. If for some reason the data wasn't written to the cluster, we can always backfill it using the CDC during the write phase, or we can lazy load it from the database. What we will do next is that we will validate the number of items. If the numbers in metadata is different from the number in the data set, the payload, metadata always wins. The metadata is the source of truth. Same goes for the version. If you read, let's say, from 5 clusters, and 4 of them return version 5, and only 1 of them returns version 6, that one cluster wins. Upper version always wins. Then the question is, how many clusters do we need, actually? One cluster is inconsistent. We already know why. One required, which means that with one cluster we expect one successful write and one successful read from that cluster, is not highly available because we use write-through. If we fail to write the metadata, we fail the request. It is not reliable. So that doesn't work. 2 clusters, 1 required. That's highly available if we require only one successful write, well, successful write in one cluster, but that is not strongly consistent because if we get the data from the cluster of single cluster, we may get the stale data. We don't have other cluster to run to act as a mediator. Doesn't work. 2 clusters, 2 successful writes or reads required. That is strongly consistent, but it is not highly available. I would even say it's lowly available. I mean, you have 2 clusters independently hosted with its own SLA guarantee, and you rely on them both. If you multiply, I don't know, if your reliability of your Redis cluster is 3 nines, and you have 2 clusters with 3 nines reliability, I think the best that you will get is 99.7 or 8. Mathematical genius, please correct me if I'm wrong here. So that doesn't work either. 3 clusters, 2 required. Highly available if we only require 2 successful reads or writes. Strongly consistent we can perform mediation. Very expensive. We multiply the data 3 times. And if we want a very high cache hit ratio, we will have to store a lot of cache data with as long as TTL as possible. So that's very expensive, although it works. But we rely only on the metadata to act as a mediator, to guarantee the validity of the cache. So we can have 2 clusters that will have the full data, metadata plus payload, and we will have 1 metadata cluster only. It is still expensive, I mean, don't get me wrong. You duplicate data 2 times, it's still too much, maybe. But it is not as expensive as multiplying data 3 times, I mean, let's be fair here. It is strongly consistent, it is highly available. Not that expensive, so we can live with it. Now the question is also how many data do we need to store in the cache? How much user entries we need to store? How many users do we want to store? So I am afraid I cannot give you that answer right now. I can only express how we figured out what would be the best case for us. We used our logs and to identify unique calls for customers, for users, which gave us an understanding how many users are regularly interacting with the storage. And we did some mathematics on that read data sets, logs and stuff, to find out that if we want to achieve 99.9 cache hit ratio, which is acceptable for our case, that's what we want, we will have to store the cache item for 3 days, 70 hours to be precise, continuously updating on write, backfilling if not on write. And in our case, it's going to be 600. So for the database of 5 terabytes, you have 600 gigs of cache per cluster, which is not too much, I don't know. But again, it all comes with the cost. I mean, when you have Redis cluster in the wild, you have to live with its limits. If you try to abuse Redis limits, you get another limits. Solution works for specific data models, first of all. The data model that I have is a basic key value, not hard to cache. I mean, I could put the same key value in Redis and just live with it. If you use relational data sets, if you use some exotic databases, I don't know, maybe you do, maybe not, the same logic of caching may not work for you. Because of the data duplication, the solution is expensive. It is expensive with regards to the storage. It is expensive with regards to the network calls. We write many times in multiple places. The solution relies on write-through. If I pick another write-through cache for DynamoDB, which is DAX, DynamoDB Accelerator, DynamoDB Accelerator will never fail the write because it couldn't write into the cache. It will fail only if it failed to write to the database, which makes sense. Write-through cache which fails when you write to the cache, but you successfully write to the database seems irrational. So you want to think twice if you want that. To achieve high cache hit ratio, we need to backfill the data as soon as possible in order to avoid the time range when there would be a cache miss. In our case, it's easy. We have CDC, we have change data capture. As soon as the database entry appears, we can read the event stream and just backfill the cache. It will be the same cache write with a lag of maybe a second or two, which is tolerable. But if you don't have that, well, you need to find another way to backfill it. And it still doesn't work, folks. I'm so sorry for that. You may leave now. If one cluster is unavailable during read, and 2 clusters are in event of resharding, you cannot do mediation. Your metadata is inconsistent. There is a chance that you will get eventually consistent data. I cannot give the number, what is the chance, how high are the odds, but it is possible. That's the only scenario where it is possible. So one option would be introduce 2 more clusters maybe, but then if you're hosted on the public cloud, your bill goes sky high. So that's the issue that we had in the result. We still cannot 100% guarantee. We can introduce 10/9 of guarantee, but not 100%. So in case if you were enjoying coffee or didn't pay too much of attention, high-performance systems, write-performant, read-performant, support that low latency and high performance with an eventual consistency as a trade-off. ScyllaDB is fast because it implies asynchronous replication, and you need to write to some number of replicas, but you read from others. Same goes with DynamoDB and Cassandra. Not applicable to ACID-compliant databases or strongly consistent databases, but that's the cost of the high performance. If you cannot achieve strong consistency with one node or one cluster of eventually consistent storage, just multiply it and apply some mediation rules. But remember that it comes with a trade-off. It always comes with a trade-off. In distributed systems, in modern industry, in software industry, every single thing you want to build always has a trade-off. Whenever you build design, you will never have, we have this system. It's a piece of legacy. I don't know what you thought. And we want to build this new shiny system, which will not have problems of this piece of legacy. Bad news is it will have another items that your successors in 5 or 10 years will call a legacy. So think twice if you want to do that. If you are curious about the theory behind consistency, distributed transactions, and distributed systems as a whole, I highly recommend the boar, the kabanchik, Data-Intensive Applications, the book authored by Martin Kleppmann, who is one of the most and maybe famous and known distributed systems experts, particularly distributed storage experts in the industry. I highly recommend that book. It is very hard to read because it is heavy with academical vocabulary. It's written by the PhD, I mean, come on. And it is a drama. Every single chapter tells you that this doesn't work. You read 100 pages that this is how you can fix this, and then the last paragraph, but it actually doesn't work. Let's clarify it in the next chapter. And like, Jesus, so much suspense. If you don't feel like reading a heavy academic material, I also recommend Distributed Systems for Practitioner. It is written by another distributed systems expert, and I'm sorry I forgot his name. I mean, I should just have written here. But you have the link. So I recommend you to go there, get the book. It is available on LeapUp, so it's distributed only in the electronic form. Please support the author. He wrote a great material. The book itself doesn't replicate, but follows the same explanation as in data intensive. You have the explanation of linearization, time, serialization, serializability of the data, CAP theorem, the trade-offs, the atomic clocks, the tweaks when you have two nodes with a tiny nanosecond difference and how to overcome it, distributed transactions, consensus algorithms, everything that brings joy if you have nothing else to do. I thank you very much for your time. Thank you. I will honestly appreciate if you can follow this QR code and tell me what you think, because that's the only way for me to become a better speaker. I mean, I don't know a problem if you don't tell me. Let's be honest here.
Questions?
Karan, first, my name is Evgeny, YDB. First of all, thank you very much for a very exciting talk. It's a very elegant solution and a very joyful presentation. It was a pleasure to listen to you.
Thank you.
And unfortunately, my question is kind of stolen. So I would like to say sorry to the original author. He also tries to raise his hand in purple T-shirt. So if you start to write your system today from scratch, what would you make? What solutions would you choose? Would you simply use YDB or other good distributed system, or would you still use your current solution?
Amazing question. So if I get this right, if I will go back in time, or actually I bring the system in the current time, and I can make a decision on a different storage backend instead of DynamoDB. Is my question right? Yeah, okay. I think the original engineers who built the system had very good justification to choose Dynamo. The problem itself is not the storage backend. The problem itself is that the system grew not in a way its developers expected it to grow. So if I would be able to change anything, I would apparently change the primary key to avoid hot shard. I would still use Redis or Dux because it comes with it supports the same DynamoDB driver, so I don't even need to rewrite anything on the storage logic, on the low-level logic. And I will work closely and heavily with the stakeholders of the storage to be able of tolerating eventual consistency. Because in fact, in production, the lag of having the actual entry after initial creation, because when you create an item, there are a lot of manipulations, and then it's not touched for a very long while. So the longest lag is, I think, 2 seconds. If all the systems that rely on the strong consistency could just wait 2 goddamn seconds, I would use a single Redis cluster or even Dux. I mean, just Dux is, come on, clickety-click, clickety-click-click-click, or run Terraform apply, change the URL, and you're done. I mean, and all the effort of engineering hours is just saved, which is money, way more than the storage itself. Thank you for the question.
Hi, I have a quick question. I must have slept through slides 13 to 18 or something like that. I'm not quite sure what the metadata cluster stores.
The metadata cluster stores the version number of the item.
Just the version number. So it's basically the IDs and the version numbers, but not the payload.
Careful, we have a very focused, attentive viewer.
Oh, squirrel.
It's very good. So you notice that I only have the latest version as a sorted set. So what's the point of, I know you told me not to come, so what's the point of having this latest version? I could just use the item ID because I only store the version, right? But what if I want to also have a nice and usable way? What just happened? Thank you. So what if I could have, I would also store the deletion marker, the Boolean value. I can also say sorted set, user ID, item ID, deleted. Yes, false, true, false. And use the same GT. That helps me to apply server-side comparison, so I don't have to do it on the client. I'm protected from the network lag and network interruption. And I can also read all the sorted sets. Deletion marker, if some extra mediation arguments I want to introduce in the future, anything in that form of the sorted set using zrange. So give me all the items with all the metadata. This one is particular for the example, but I can store more.
Okay, got it, thanks. That's exactly the slide I slept through, thank you.
I love this intention. Okay, you're good. You can continue. More questions, please. Raise your hands.
The folks just want to have alcohol. Don't block them.
Please.
Hello, thank you for your talk. And I maybe missed a part also, but do you make some replication or synchronization between 2 data clusters you use? Because if not, as I understand it, once you write your data to metadata cluster to one data cluster, and then another write fails for some reason, you only have data stored on one cluster. And if it later comes unavailable or resharding or anything, you just don't have your data. And how do you solve it?
That's a good question. We do not have inter-cluster replication. What we do is actually, I want this slide. I should have drawn these errors nicer. The caller writes to all the clusters within a single write operation on the storage. That means that if I'm the storage service, I receive a create request. I will go to all the clusters and say, write this, write this, write this, and I rely on the metadata. This is why it is important to get the successful number of writes and reads, at least 2 in our case, which is the most efficient. I attempt to write the metadata to 3 clusters. If I succeed in 2 times, at least with 2 clusters, I'm good. If I succeed with only 1, that's not enough. I need at least 2 if I have three nodes as a mediation. With the payload, the data, the problem is not present because the metadata is the mediator, and if it somehow conflicts with the payload, I invalidate the cache immediately, lazy load it, and serve it to the client. So I don't necessarily, the payload is not necessary for mediation. The metadata is important. That's why we need to keep it slow and shrink as much as possible. Thank you for the question.
Please.
Yeah, the question is about how does your system, especially the metadata class, possibly handle Byzantine faults? So it looks like if something goes wrong with your metadata cluster, then it's all gone. Because
what do you mean by if something goes wrong with the metadata cluster?
When something goes wrong, the metadata version gets written wrongly, for example. It's not the latest one, the data is corrupted, something like that.
So if something rapidly appears in my network, corrupts all the data in the metadata clusters?
Metadata cluster. How do you do refill it from other data, or what happens?
Oh, that's a very good one. So imagine that I have the payload version 10. The versions are always incremental, right? So I have the version 10. And someone sneaky comes into my database, or a cluster in that case, and changes the metadata from 10 to 9, right? Is that do I get the question right?
Yeah.
Okay. So in that case, that malicious actor needs to know the topology of the cluster. They need to have access to all the clusters. They need to know where to go, what to write, successfully do that. Or they need to abuse the code that I have, which is kind of built, I mean, it's compiled in a binary. But okay, let's say that happened. What I could do, I could assume that the metadata cluster metadata is invalid, and I could say that the version, if the version in the metadata is lower than the version in the payload, something is very off, because in the most common case, I would expect it otherwise. I would expect that the payload version is lower than the version of the metadata cluster. I think what I would do, I would return an error. And if someone is messing with my cluster, I will have a lot of errors. And the problem is not if the cluster cannot suffice the read. We do not return an error if we fail to read the cache. We just invalidate, we assume that the cache is invalid. So the worst case scenario, if I think about it a bit more, we cannot search the cache. We need to wipe it all, do an investigation, because I'm pretty curious who in a normal business as usual scenario would come to my storage and mess it up. I mean, I can hardly imagine that happening. But in that case, we have no cache. We have to go back to the database and again suffer from hotshots and such. But yeah, the caching system is not tolerant to malicious actor. That's a good one.
Okay, you, and then you. So we have a triangle of questions over here.
Okay, following up the previous question, it could be a bit flip, which happens like once in a trillion times, but it could still happen. You would get a version 8 instead of version 10 because of a, I don't know, hard, high-speed particle which hit your M module, and you got a bit flip.
I would love to learn more about it. Can
Yeah,
you tell me
I mean,
outside of the
it
presentation?
never-
Because I would love to. Because I will compile your words into the document and throw it at my colleagues.
Yeah, just for fun, because it never actually
Thank
happens.
you.
But I
The
have
fun is the best argument.
Right. Indeed it is. So, just for fun, yet another question which kind of resembles the previous one. As you mentioned, and as the Kabanchik says, everything fails. So, what was the most spectacular failure that you have experienced with this particular system so far?
My favorite AWS outages, of course. But that's something that we cannot solve. I mean, the system itself is tolerable to almost everything. It is well written. The code review process and the production readiness process strongly implies having a very hard and heavy suite, testing suite, to ensure that all the calls are valid and nothing in practical happens there. And yeah, I would say hardware or network issues are the ones that happen the hardest to the system, because the system is the basic root. Create, read, update, delete. It's not expected to do any logic, business logic.
Right, but what was the most spectacular failure, maybe hardware related? Like, all right, we had this one time when the entire record storage just went away.
I have to disappoint you. The AWS outage or a network outage on the cloud provider side was the hardest one. I don't recall anything more fun. So that's boring.
Boring, yes, indeed.
Yeah.
Sorry.
Apologies for that.
Sorry, yes.
Could you-
I'm sorry for you too.
Could you pass the microphone on the third row, please? Thank you.
Yep. Thank you for the talk. And I want to follow up with the first question and ask you, have you considered any databases with supported quorum reads and writes? So why write your own quorum reads and writes?
That's a very good question. During the evaluation of the design, we found out that using a different database, let's say supported in the company, officially supported and maintained in the company, with migrating the data, migrating the readers and writers, and you know that with 30,000 requests, read requests per second, it's very hard to migrate the readers without customer impact. With the cost of migration effort and the double cost during the migration, we found out that it would be cheaper to maintain, to build our own caching system on top of Redis rather than migrating to a different, maybe faster database that doesn't have hot charts.
Am I correct? So you had your Redis cache in the first place, and then you developed the quorum reads upon that.
The logic was developed on the service side. So we have a service which communicates with Redis. We have Redis as a provided service, just click, 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 click. And we build the logic inside of the application.
Okay, I
and
see.
work with multiple Redis clusters.
Thank you.
The timer says 0. What am I supposed to do? I can answer a few more questions if that's okay.
It is an information. It is the information for me.
Okay.
So it's okay.
I don't disappear. I'm not going to vaporize. So you can ask me questions afterwards outside.
No. This is for me. It's because I'm a 0, but we love you. Please.
Hi, my name is Anton. I work in YDB. Thank you very much. It was fun to listen to you. I just didn't get one thing. What happens when the write to Redis clusters fail? Not because 3 of them are unavailable, but because the write fails itself. So it writes to DynamoDB, and then everything.
The metadata write? Or the payload write?
When the first section is successful, so DynamoDB put item is successful, and then the write fails completely. So it doesn't.
So we written the metadata in the Redis in all the required amount of Redis clusters. Then we successfully wrote to Dynamo, and then the call fails here on writing the payload.
Yeah.
We will log an error, obviously. The consumer that consumes the CDC event stream during the validation of the cache will see that the payload was not written and backfill it. If it doesn't backfill it, we will backfill it during the read request on the same entry using lazy load caching strategy.
So do I get it right that when you will try to read the data, you will check the metadata, will not find the correct version in caching service, and go directly to DynamoDB?
We read the metadata because the metadata was written successfully, otherwise the call would fail earlier. Then we read the actual payload. We do the validation of the payload, comparing the version. If the version from the metadata is higher than the version of the payload, we invalidate the cache, lazy load, serve to the caller. We read from the database in that case.
Got it. Thank you very much.
It's all it all doesn't work if you have poor cache hit ratio. So you need to support high cache hit ratio in order to make it to production. That's why persistence of cache is important.
Vladimir, please.
Please tell me you're not from YDB.
No, he runs a different database.
Okay. Oh, come on. Okay.
It looks like a big spider.
Tarantula. Hi.
Yes, I'm Mons, and I want to dilute some YDB with Tarantul. The question is, what is the source of truth for version? Is it external data, or you generate a version as an increment based on distributed several clusters of Redis?
I need to go a bit deeper on the database side, so we need to go in this slide. Click.
We have 20
Yes.
minutes till the next talk.
Okay, okay.
Take your time.
So we don't have caching system does not exist. We have Dynamo, we have the service. The service says, hey, please, service receives a call. I want to write the data. The data is not present in the database. It's a create call. The version begins with 1 because the data is not present. We know that the data is not present because we read the data from the database using the get item, supplying with the primary key. We don't get the data, which means the data doesn't exist. We create. We choose the version here. We produce an event, item created, user ID this, item ID this, version 1, blah. Next one, I want to update the entry. We get an update call. The caller doesn't know the version. The caller just say, hey, please update this item for me. We check if we do the update. Sorry. We read the data in a transactional mode. DynamoDB supports transactions. So we do the transactional get. We know that the version is 1.
So for
We
your
initiate
system,
the-
I'm sorry. For your system, the source of version is DynamoDB.
Correct.
Okay. Thank you.
We don't do any magic there. It's boring. I
Wow,
love it.
that was fast. I was expecting a longer conversation. Over here, please. And then we'll need to pick whoever gets the prize for the best question.
Hello. How often do you hit the throttling from the DynamoDB service, and how do you handle that?
Too often.
And
jokes
is-
aside,
is the exclusive reason that you
Yeah,
built
the
the cache because you hit that throttling?
Okay, so in caching we don't get a hot shard because the Redis has a much higher throughput with regards to requests than Dynamo. And also throttles from Dynamo come from the API. It's not that the database is like, it's the API telling, dude, back off, please. I have other tenants, other customers, whatever. So the core reason of having throttled is what happens when you run a list items for a given user, and if a user has more than 1,000 entries. And it was not assumed in the design. It was assumed that a single user may have maximum 10 items. That's the assumption that the design was built around. And then suddenly we have a user who has 27,000 items. And every time they will do anything, we got 27,000 read requests on the Dynamo, which is being punched. And this is the event when we get hot shard. Another event of the hot shard, which is an assumption. I assume that sometimes there is some network outage or internal outage happening on Dynamo because from the CloudWatch logs I have the 500 internal error. That means that DynamoDB got an exception which it couldn't translate to myself for the human readable form. So I assume there was some network issue or a hardware issue happening on the AWS side. I don't know. I'm not an AWS developer. And when the master node, the leader node was moving to another node, the leader promotion was happening. The replica was receiving read requests from another to fulfill the data, plus it starts receiving the request from me. I also assume that could be the reason of the hot shard, but that's underlying, I don't know. But the most cases, yeah, if you have a user with 1,000 items or 3,000 items or more, you are risking to have hot shard on Dynamo. Because we use strongly consistent reads, so we write to the leader and we read from the leader.
It's good to have you with us. Thank you very much.
My
Thank you
pleasure.
for your talk. Hold on. So, who gets the prize for the best questions?
Of course, oh my gosh. All right.
Or maybe your Uber.
The guy
is
with the
here,
click
so-
house t-shirt abusing my Redis cluster. I don't like you. I have to talk to my engineers now.